All right, here we go. So we want to first draw the influence line for this problem, and then find the maximum effect due to a set of live and dead loads. So you can see from the problem description that I want to find the maximum positive moment at D. Okay, so I'll draw my qualitative influence line first. So I'm going to assume that I have this hinge at D, and that we're going to put positive moment. Everybody see that? So I'll draw a graph, and we'll say the moment at D as a function of x, and I'll slide all these key points down so we can see it. There we go. So what's going to happen when I apply that moment at D?
It goes up.
D is going to move up. So I think you can see that off of E, it'll move up quite like that. Then it's going to seesaw over C, right? So if D goes up, B is going to go down. Oh, my graph is out of whack. And then it'll hinge at B and go back up to A. So there's my influence line for the moment at D. So what value do you want to find? I think it might be easier to find this one. So what I have to do now is rework the original problem. So let me draw that over here. So I have a hinge. I may not get this completely correct. Let's see, I got AY, so I'll have a reaction in the Y direction. I've got CY, and I've got EY. And then I'm going to put this unit load here at D. So I didn't get it to scale right, but this will be 5 feet, 5 feet, 5 feet, and 10 feet. So see, I'm applying the unit load at this point on the beam. See that? At point D. And I want to find the moment at D. So what's the easiest way to do that? Well, I would cut a free body diagram, right, at D. And if I look at the right-hand side, all I need is EY, and I can find the moment at D, right? So how do I find EY for all that stuff? Well, I can't sum moments at A, right? Can't sum moments at C. It seems like no matter what I do, I'll have one equation and two unknowns. So I'm going to have to break the structure apart here. Right? So if we go over to this side and I look at a little piece of the free body diagram, this left piece, and I have my reaction at AY, and if I break it apart here at B, I would have BY and BX. But notice there's no load there, is there? Because the load's over here. So what is AY? What is BY? There's 0. So that was easy. BY is 0. So now I can work the right-hand side. Let's see where I can fill that. I'll put that here. So here's the right-hand side now. This is B. Oh, sorry, I've been doing blue. Here's CY. Here's EY. Here's my unit load. And of course, BY is 0. So can I find that now? Can I find AY? I'm sorry, EY? Yeah, sure. I just sum moments about C. So I'll come over here and sum moments about C. the unit load will create negative moment at a moment arm of 5 feet, and EY will create positive moment at a moment arm of 15. So EY is equal to 1/3. Okay? And if I know EY is 1/3, I can put it back in there, and I can sum moments now at this cut surface in equilibrium, and what do I have there? Well, my internal moment MD is negative. EY creates positive moment of 1/3 times 10 feet. So the moment at D is 10/3. And again, it has this funny unit of feet. So I go back over to my influence line, which now has units of feet, and I know this value is 10/3. So what's this value? 10/3 is to 5 as what is to 5? 10/3. So this is negative 10/3. And now I have my influence line. That wasn't so bad, was it? So now I have my influence line for the moment at D. Any questions about that? So now I'll apply it. The problem says we want the maximum positive moment that can be developed at D. So first we have a concentrated load of 4 kips. So where do I put my 4-kip concentrated load using my influence line for a guide to create positive moment? I don't want to put it here. That's negative, so I put it here. So that means that for the concentrated live force, what do I get? I get 4 kips times 10/3 feet, which is 40/3. 40/3 is 13.3333. Is that right? So 13.33 kip feet. Okay, the second thing says, let's do the dead load first. So I have a dead load of 200 pounds per foot. How does dead load work? It's uniform load. So I have to take the area under the curve times the value of the load. So let's do the dead uniform load. Unfortunately, I had this Monty Python skit rolling in my head where they say, "Bring out your dead, bring out your dead." You guys ever see that movie?
Yes.
Yeah, sorry about that. No, you should. It's very interesting.
Very British. No, that's not my thing.
It was during the Dark Ages, so people died quite a bit, so a little push cart would come by in the morning and collect the dead. And the little guy would yell, "Bring out your dead, bring out your dead." And they threw some guy in the back. He says, "I'm not dead yet." So they hit him in the head. "You are now." You guys should watch this. Anybody know who Monty Python is?
I started watching it a bunch of times and didn't make it through because it's so dumb.
Well, I'll give you a little history lesson. When that show came out, nobody had done anything like that before. Of course, now all comedy is like that. Like this is how Saturday Night Live got started, was Monty Python. So I think they stopped in like the late 60s. It's really old.
Wait, I thought it was movies.
Oh, they made movies after the show.
Oh, there was a show?
Oh, yeah.
No, I never heard of the show.
Oh, mid-70s. It was good. It got kind of weird at the end, but when they first started, it was pretty funny.
It got kind of weird at the end.
It started off weird.
Okay, so back to this. Let's bring in our dead load. So we're going to take the dead load, which is 200 pounds per foot, and we're going to multiply it by the total area. Now these are two triangular shapes, so triangles are always 1/2 base times height. So we'll start with the first one. What's the base of this triangle? 5 and 5 is 10 feet, and that height is negative 10/3. The area under this part of the triangle, again, is 1/2 base. That base is 15 feet, and its height is positive 10/3. So you guys are going to have to help me with that. I don't think I can do that off the top of my head.
The wheels are turning.
I don't know. I can't do it. I lost track. I lost some decimal points in my calculation. Basically, this is just positive 5. So this is 50 over 3, 50 over 6. What's 50 over 6?
I got a big number.
It should be 50 over 6 times 200.
Yeah.
1666.
What'd you get?
Can we interrupt your class for 5 minutes?
I'm recording. Can't right now. You can interrupt in about 2 minutes.
I got 8.33.
Now this is in pounds, right? So
I got 1666.
we want to convert it back to kips,
One's negative, remember.
right? One's negative and one's positive. So this is just 10 of those and 15 of those, so it should just be positive 5 of those. That should be 50/3. Divided by half is 56.
1666.
1666.
Let's miss up.
So and divide that by 1,000.
1.66.
1 point what?
666.
Okay, 1.67. This will be kip feet. Okay? Now this is something we haven't done before, so let's pay close attention to this one. This is going to be a live uniform load. We haven't done live uniform loads before. So another skill, live uniform load. Now, live uniform loads, you're allowed to start them and stop them wherever you want. They don't extend across the entire structure. Dead loads are across the entire structure. So where do we start and stop a live load so that we capture the most positive moment? Well, that would be the area of the curve that's all positive. So I'd start my live load at C and extend it to E only. So when I did that, the value would be 300 pounds per foot, now times the area of this positive area. So again, it's triangle 1/2 base. The base for this one is 15, and the height is 10/3. So what's that? That's 150 divided by 6 times 300.
7,500.
So that would be 7.5 kip feet. So what is the total moment at C? Would be the sum of these three things. So if I add that, I get 15, right? And add that, I get 22.5.
What did you just say?
I just added these three together. 13.33 plus 1.67 is 15, right? 15 plus 7.5, 22.5? Okay. Now just so you can visualize that, I'll redraw the beam. And I'll put the reactions on. There's A, C, and E. Now, across the whole structure, I get my uniform dead load. I'll just write DL next to it. Over the part of the structure that's positive, which extended from C to E, right? That's my live load. And then where was the concentrated force? computer just died. It was at D. And D on this diagram is about here. So there would be my 4 kip load. This is the 300 pound per foot load, and then the dead load is 200 pounds per foot. So that actually kind of gives you some idea of the loading that produced the maximum moment at sea. Any questions about that? We'll probably work some more of these.